Hey, what's going on, y'all? Sean here, with a calculus video on what's called Fermat's theorem. Hopefully, I'm pronouncing that correctly. But before we get into this, make sure you like the video, make sure you subscribe to this channel. Um, yeah, and let's just go ahead and get into it. All right. So, Fermat's theorem says the following. So it says if f, some function f, has a local max or min, that's a maximum value or a minimum value for this function at some point C, and f prime of C, or in other words, the derivative at that point C exists, then um, f prime of C equals zero. So let's read that again. So if some function f has a local maximum or minimum value at point C, and the derivative at C exists, then you can say that the derivative um, at point C is equal to zero. Okay. So if there's a maximum or a minimum at C for a particular function, and then the derivative exists at that function, then you can automatically know, per se, that the derivative at that point is equal to zero. Okay. All right. So the purpose of this video is to go through the proof and make sense of it. All right. So here we go. So first of all, let's say this. F of C is greater than or equal to f of x when x is close to C. Okay, so what is it saying? The function at point C is greater than or equal to the function at any point x when x is close to C. So in other words, that's just saying that as you get close to C, then the function is going to be greater than or equal to the function at any other point. Okay. All right, next. So if h, some value h is close to zero, so h is positive or negative, then the following is true. So f of C is going to be greater than or equal to f of C plus H. Okay. So let's read this again. So if some value H is close to zero, okay, so that means it's a very small value, and that's H is positive or negative, but it's something very small, so it's close to zero, then F prime of C is going to be it's going to be greater than or equal to F prime of C plus H. Okay. So that means you're getting really, really close to the function at point C on either side. Okay. The next thing is you can kind of move this around a little bit. So if we were to move this to the other side, so in other words, I'm sorry, if we were to move this to the other side, what happens is you have F of C plus H is going to be less than, I'm sorry, I didn't write it all, minus F of C is going to be less than or equal to zero. Okay. So all we did was just move that f of c to the other side. So the function at c plus h, so that's some value that's very close to um zero for h. So it's something right close to c, and you subtract f of c, it should be less than or equal to zero. Again, that's because we know that the function is going to be greater than or equal to the function at any other point. Okay. Now, next point. If h is greater than 0, so in other words, if the h value chosen is positive and is sufficiently small, then okay. So then we're going to take this right here and we're going to divide it by h. So f of c plus h minus f of c divided by h is going to be less than or equal to 0. So what we've done is we have divided this portion here by h, given that h is positive and is still very small. Because it's still it's very, very small. Think about it. If it's small, then that means that, for example, if this were big, then it would be substantially lower than substantially lower than 0 this side of the inequality. But we've chosen an h that's very, very small. And so we're still kind of close to where we were to start with. Okay. All right. So let's keep on going. All right. The next point is now we're going to incorporate some limits. So the limit as h approaches 0 plus, that means as h approaches 0 from the right. So positive values on the right side of 0, 1, 2, 3, 4, 5, 6, 7, as so we're going back toward 0 from the right for this stuff here. So f of c plus h minus f of c over h. That should be less than or equal to the limit as h approaches 0 from the right of 0. Okay. So all we did is take the limit of both sides, the limit as h approaches 0 from the right. And so what is that equal to? That should be equal to 0 because the limit as h approaches 0 from the right for 0 itself is going to be 0. So since this limit is 0, then this limit must be equal to 0 as well. Okay. All right. So now we can say that since f prime of c exists, we can say the following. Let's scroll down here. If you need stuff, just rewind the video. We can say that f prime of c is equal to the limit as h approaches 0. Notice we don't have a plus or minus of f of c plus h minus f of c over h, which is equal to the limit as h approaches 0 from the right of f of c plus h minus f of c over h. Okay. All right. So let's make sense of this. So we know according to Fermat's theorem that the derivative at point C exists. So because we know that limit exists, we can say that the derivative, which is going to be equal to the limit as h approaches 0 from both sides, should be equal to what we just found here, the limit as h approaches 0 from the right side. And we're able to say that they're equal because the derivative exists. Remember, for the derivative to exist, the limit from the right and from the left have to both be equal to the same thing. Okay. If the limit approaching from the right is one thing, the limit approaching from the left is another thing, then the derivative, we can't say that the derivative exists. Okay, so hopefully that makes sense. So this shows that the f prime of c equals 0 because remember we know that that right-handed limit is equal to 0 from this step above here. Okay, so the next question is, what if h is less than 0? So this was when h is greater than 0 but sufficiently small. What about when h is less than 0? Now keep in mind h is that denominator. So we had an inequality there. Remember that the inequality flips. Okay? Because what happened is, let me scroll up here. Over here, when we divided this by, I'm sorry, this step here, when we divided this side by h, we divided both sides by h. We did the same thing to both sides. But when you divide by a negative h, this inequality is going to flip right here. Okay. So what happens is you have this f prime. I mean, no, I'm thinking too quickly. So it's going to be f of c plus h minus f of c over h is going to be greater than or equal to 0. This is in contrast to less than or equal to 0 in the previous example. Because again, the h that we're dividing by is less than or equal to 0. Okay. All right. So let's keep on going. Yeah. All right. So we're gonna take the limit. So the limit as h approaches 0 from the left of this stuff is going to be um equal to, we're kind of skipping steps here because it reflects what we did previously. Um f prime of c, which as we know will be equal to the limit as h approaches 0 from both sides of f of c plus h minus f of c over h is going to be greater than or equal to 0. Okay. So like I said, we skipped a couple of steps here. All we did was, so when we flip the inequality, now we are, because we know that we're doing h um less than, let me see, less than 0. H is approaching 0 from the other side. And therefore we're taking the left-handed limit this time. But if you go up here, we know that the left-handed limit, because the derivative exists, the left-handed limit is going to be equal to the derivative, which is going to be, of course, the limit as you approach h from both sides, which is going to be less than or equal to 0. Okay. All right. So this shows that the derivative at point C is less than or equal to 0, and the derivative at that point C is greater than or equal to 0. Therefore, we can say that the derivative at point C is equal to 0. Or in other words, the derivative at a local max or min is equal to 0. Okay. So we've essentially proven that Fermat's theorem, um, we've just proven Fermat's theorem, which again, let's go back. That Fermat's theorem was that if you have a local maximum or minimum at point C and f prime of c exists, the derivative exists at that point, then the derivative is going to be equal to 0. Okay? All right. Very good. So just keep in mind that Fermat's theorem may not apply to certain kind of things. So for example, what if you had, and I just do a rough drawing of it. What if you had this here? Change the color. Oops, actually, that's not a good drawing of it. So let me try that again. Let's go like this. This is an x cubed graph. Now, what about if you were trying to take the derivative of this? Now look at this. This is f of x equals x cubed. F prime of x using the chain rule is going to be 3x squared. What if we're trying to take the derivative at point 0 right here? So f prime of 0 is going to be equal to 3 times 0 squared, which is 0, right? However, is there a maximum or a minimum here? The derivative does exist, but is there a max or a min here? No. So Fermat's theorem doesn't apply here because there's no max or min when you actually graph the thing, right? Give you another example where Fermat's theorem doesn't apply. Say, for example, you have this thing here. So again, rough drawing. This is f of x is equal to the absolute value of x. Now, if you look at this graph here, if you look at this graph, there is, if you look at f of 0, visually, this is a minimum, right? That's a minimum. But what about the derivative? The derivative, if you look at here, you remember the derivative is a slope. If you look at the derivative here, you take the derivative as you approach from this side, it's going to be all along here, the derivative is going to be equal to, it's going to be negative. And then along here, it's going to be positive. So in other words, the derivative at this point does not exist. The derivative doesn't exist at this point. Okay. So f prime of 0 does not exist. So in other words, that means it's important to, you know, to consider this. You can look for maximums, and minimums where the derivative at a point is equal to 0. So look for it because it's likely that Fermat's theorem applies, and wherever you find the derivative equal to 0 is a maximum or a minimum. However, it doesn't necessarily guarantee. So that's why it's important to consider all factors. Is it visually a minimum or a maximum? And does the derivative actually exist? Okay. All right. So that is the proof of Fermat's theorem. Hopefully this was helpful to you. Um, Continue to follow me by subscribing and also help me out by liking this video. And I hope you have a good day. Hey, thank you for watching this video. If you need math tutoring or you need SAT math help, look in the description to find out how you can sign up today. Also, don't forget to like, share, and subscribe so you stay in touch with Math Swap Tutoring on YouTube. Have a good one.